what all the specific issues or specific features that are important in the consideration of or in the analysis of hypersonic flows. Now, the importance in analysis is strongly related to importance in design as well. So whatever all the specific phenomena that we are going to look at here, they will again during the course, they will again surface when we discuss analysis and also when we consider some of the design aspects. So that's the importance of the topics that we are going to look at right now. Today we will be looking at four important aspects of hypersonic flows. In fact, these are the four physical phenomena that characterize any hypersonic flow application. Anything that is above Mach 5, you are going to have all the four that I have listed here, which are the thin shock layers, entropy layer, viscous interaction, and high temperature effects. So thin shock layer, entropy layer, viscous interaction, high temperature effect. These are the four phenomena which are sort of unique for hypersonic flows, and they always, any hypersonic flow application will have more or less of all of these effects to some significant or considerable extent. Now, usually people add one more in this list, which I'm cautiously avoiding. We will be addressing that later in the course. That is rarefied flows, rarefication of flows. In fact, rarefication of the flows is not a rarefied flows where you have Knudsen number being the parameter to determine whether the flow is rarefied or not. That is not an inherent property of hypersonic flows. People consider rarefied also along with this four. That is because of hypersonic flow applications in space propulsion systems. So only beyond the atmosphere, where the density becomes gradually lower, lesser and lesser, the rarefication effects become important. So since in such situations you have the hypersonic vehicles as well as rarefied gas, you have to consider the combination of the two. But otherwise, in hypersonic flow, rarefication cannot be considered as an inherent part of it. It happens only when you go beyond the atmosphere. So that's the reason why I limit our attention to these four, which can happen anywhere. Even if you have a hypersonic tunnel, hypersonic test facility in the laboratory, you will have to encounter all these. So you will have to address all these one way or the other. So these are unique characteristics of hypersonic flows. We will be looking at each of them with some details right now. First, the thin shock layer. I want you to be reminded about the oblique shock theory. In fact, later in the course, we'll be quickly reviewing the oblique shock relations and oblique shock concept, because we have to keep using them all the time. So soon, in the next few classes, in one of the next few sessions, we'll be reviewing the shock theory. But please be reminded that whenever you have a compression corner, you will have a shock formed, and to some extent, it can be attached shock. Like all the pictures that you see in this particular slide, they are all attached shocks. So if you have a reasonably sharp corner, you will have a shock when supersonic flow encounters. Now, here we are not talking about, this need not be that is formation of an oblique shock, we know need not be in hypersonic flow. It can happen in any supersonic flow. So oblique shock formation is common to supersonic and hypersonic flows. What we are talking about here is thin shock layer, which is specific to hypersonic flow. So we will try to understand what it is. Now, what is shock layer? Shock layer is the flow field between the shock wave and the body. So please be clear about that. So for example, in this picture, I'm trying to point on this. You have the shock layer, a shock wave here. You have the body surface here. the adjacent body surface. So what we mean by shock layer is the flow field in between. So at any given section, the shock layer is this. Say if I'm looking at this section, this is the shock layer, and say here it is this, and similarly like this. So the shock layer is the region between the shock wave and the surface of the body. Okay, so here say in the second picture, actually, this is 1 and this is 2. In the second picture, you can see that this is the shock wave and this is the surface. So what we mean by shock layer is again the region between the two. So shock layer is the flow field between the shock wave and the body. Now, with increase in Mach number, you should again recall that from hypersonic, compressible flows, that the wave angle keeps decreasing. Now that remains, or that we should immediately recall what is wave angle. So for that, I'm just taking you to this familiar M theta beta diagram that we have discussed in detail in hypersonic flows. M theta beta. M is Mach number. Theta is the compression, the flow deflection angle, that is the included angle of the body or the half angle of the corner, and beta is the pressure wave, pressure wave angle. So in this schematic, this is beta. So you have the oblique shock, you have the surface, the angle between the main flow direction and the angle, angle between the mainstream direction and the oblique shock is what we call as beta. Whereas angle between the mainstream direction and the surface is what we call as theta. So we know that when there is actually, if you go by this shock wave diagram, it clearly comes out that when you have, for a given theta, when you have an increase in Mach number, the beta reduces. That is, say, for example, so if you these are for different Mach numbers, Mach 2, Mach 3, Mach 5, Mach infinity, etc. So as you increase the Mach number, the value of beta, what you measure on the y-axis, that keeps coming down. Okay, so just remember, we'll review this with those equations for shock wave relations, etc. later. But for now, just remember that when there is an increase in Mach number, there is a decrease in the shock wave angle for a given value of theta. Now let's get back to what we were discussing. So what is stated here is that when there is an increase in Mach number, the wave angle keeps reducing, which means that in hypersonic flows, since we are invariably dealing with high Mach numbers, the wave angle will be typically low. So the distance between the body and the shock wave is very small. That is, say say like this. The body, if you have a body like this, if you have a corner like this, corner or a body, a pointed body like this, the shock wave will be very close to the surface, or in other words, the angle beta will be close to theta. Beta will be close. Beta will approach theta as m tends to infinity. M increases. The Mach number increases. So this is an important observation. Why is it important? Because the shock layer, with increase in Mach number, shock layer becomes thinner and thin, and in such a way that eventually the shock layer tends to merge with the boundary layer. Now remember, please be attentive to what we are considering now. The shock layer is so thin that it will merge with the boundary layer. So we know what is boundary layer. We now understand what is shock layer. When Mach number is increasing, the shock layer becomes so small that it sort of tries to, or rather it approaches the thickness of the boundary layer, which means that now the shock layer becomes a highly viscous region. keep in mind in hypersonic flow, we considered the whole, in compressible flow course, we considered it always inviscid, okay, the shock formation, etc. But now in hypersonic flow, when there is an increase in Mach number and if the Mach number is significantly high, the shock wave will be so thin, or shock layer will be so thin that it will try to merge with the boundary layer. And this phenomenon is known as thin shock layer. So, for example, for Mach number, as shown here, Mach number in free stream Mach number of 36, the shock layer is, or rather, the shock angle beta is about 18 degrees when the compression angle is 15 degrees. Theta is 15 degrees. So it's just 3 degrees difference between theta and beta, which means that this region is very, very narrow. The region between the surface and the shock is very narrow. This is what is referred to as thin shock layer. Now, thinness of the shock layer, since it merges with tends to merge with the viscous layer, it can have an impact on the pressure distribution on the body. We will be discussing that later in the course, how the thin shock layers, how some of those properties are made for actually simplifying the calculations of pressure distribution along the body. We will be addressing that soon. So that's one thing, thin shock layer. Now the second is viscous interaction. What is viscous interaction? The answer is quite straightforward. Interaction between the boundary layer and the outer inviscid flow. Now, what is boundary layer? The region close to the surface. Okay, before that, let me stop for a while. Is there any question based on what we discussed as thin shock layer? No, so I hope it's clear for now. Now, viscous interaction is interaction between the boundary layer and the outer inviscid flow. Boundary layer is the region close to the wall. Outer region, that is beyond the boundary layer, we can typically consider the flow to be practically inviscid. So the interaction between the two becomes important in hypersonic flows. This is because at high temperatures, the flow temperature, at high Mach numbers, the flow temperature increases. Why flow temperature? That we are actually coming to that next. That is high temperature effects. But please keep in mind that near the boundary, inside the boundary layer, the velocity will be low. So a lot of kinetic energy will be converted to internal energy. And kinetic energy is very high because the Mach number is high, velocity is high in the mainstream. So part of it, a significant part of it gets converted into internal energy within the shear layer, within the boundary layer, which in turn increases the flow temperature. So because of the increase in temperature now, what happens to gaseous viscosity of the gases when temperature increases? Anybody, please? When you have a gas, when you heat it, what happens to the viscosity of it?
Increases.
Sorry.
Increases.
Viscosity increases. For gases, viscosity increases. For liquids, viscosity reduces with increase in temperature. So as the gas, as the air or whatever, the stream is coming at a high velocity, it has higher temperature near the wall, and because of this, the viscosity increases. When viscosity increases, the thickness of boundary layer obviously increases, because boundary layer is a region that is required for the entire viscous dissipation. Higher the viscosity, higher the boundary layer, which means that the boundary layer keeps thickening in such a way that it starts interacting with the outer region, the which is otherwise an inviscid flow. So this coupling or this interaction of the outer stream with the viscous layer, or the other way around, the growth of the viscous layer affecting the outer region with increase in viscosity and reduction in density is what is referred to as viscous interaction. So boundary layer becomes thick, and also one more thing to be noted here, the delta, the thickness of the boundary layer is 1 by square root of RE. You probably have studied that in fluid mechanics. It's inversely proportional to the square root of Reynolds number. The higher the Reynolds number, this tends to be the thickness tends to be less. Whereas Mach number, because of these two effects, that is heating as well as the increase in velocity and the further coupling with this, the relation is proportional to square. That is boundary layer thickness is proportional to m squared, and it is inversely proportional to square root of RE. So a relation between the two or the three is that boundary layer thickness is proportional to m squared by square root of RE. Again, so this is there is a strong dependence, that is delta being proportional to m squared indicates the strong coupling between the boundary layer thickness and the Mach number. Now, which means that the boundary layer grows very rapidly, which in turn means that the drag will be high. The viscous dissipation will be high, and the boundary layer will start interacting with the invisible flow field. And because of this, all the aerodynamic properties, drag, stability, and also the lift, etc., will be significantly impacted. This is one reason why in the design of hypersonic, in the design of hypersonic vehicles, the body and the engine cannot be independent of each other. In fact, the engine has to be part of the body. So the engine body integration, the engine mainframe integration is a major issue in hypersonic flow applications, hypersonic propulsion. As primarily because one of the factors that contributes to that is the viscous interaction. Will be again later in the course we'll be addressing about how to model viscosity, or how some of the correlations are used to model viscous forces. Now, the other property or characteristic of hypersonic flows is the entropy layer. Now, what is boundary layer? We know a region that separates, a region where the gradient in velocity is high. Similarly, entropy layer is a region in which the gradients in entropy is high. That is, you have in one region you have lower entropy, the other region you have a higher entropy. Where this happens, please look at this schematic representation here. When you have a bow shock here, we know that if the body is sort of having a blunt edge like this, the supersonic flow, supersonic or hypersonic, either way, you will have a standoff shock like this, which is referred to as a bow shock or a detached shock, etc. When you have a detached shock like this, we know that. Okay, let me ask you that. What do you mean by a bow shock? Anybody? So I have a body like this, a solid body like this, which leads to the formation of a bow shock like this, a detached shock like this. Now, what do you mean by a bow shock, or what characterizes a bow shock? Or let me make it simple. What is the difference between a bow shock and then attached oblique shock? Okay, let me rephrase this question. Is it like an oblique shock or is it like a normal shock? Somebody, please.
So it's like both.
Sorry, please. Can you please explain? Can you please elaborate on what you said now? Where is it like a normal shock? Where is it like an oblique shock? Yeah.
Sir, at the edges, I mean at the ends, sir, it is oblique shock, sir. When there is no curvature, it's normal shock.
Sorry, repeat the second part of your question. Answer. What did you say? There is.
Sir, let us say if we take a tangent to the curve, sir, near the center.
Yeah, that's correct.
It's a normal shock, sir. When you go up or down, it's a oblique shock.
Exactly. So near the center, you have a normal shock region. Away from the center, you have a oblique shock region. Okay, that's very good. So now, just based on that, just see what happens to the entropy. We know that across shock, whether it is normal shock or a oblique shock, you will have a increase in entropy, right? But we also know that a normal shock is a stronger phenomena. So the variation in entropy will be higher across the normal shock, whereas variation in entropy will be relatively lower. That is, increase in entropy will be relatively lower across an oblique shock. So normal shock, higher entropy rise. Oblique shock, lower entropy rise. Okay. Now, as you very correctly pointed out, I have normal shock here. I have oblique shock here. This means that the streamlines which goes through the normal shock will have a higher increase in entropy. The streamlines which goes through a oblique shock region will have a lower increase in entropy. I hope that is clear. That is, streamlines which are near the center, along the center, they are going through a normal shock. So they will suffer a higher increase in entropy. Streamlines which are going away from the surface, they are going through an oblique shock region. They also will have increase in entropy, but it will be relatively low, which means that now if you consider the combined region, in that you are likely to have, not likely, you will invariably have a difference in entropy between different layers, because some of them have gone through normal shock, some of them are coming through oblique shock. So there is going to be an entropy gradient. This can happen in supersonic flow also, but since Mach number is very high, the amount or the gradients are going to be strong and more prominent in hypersonic flow. So in supersonic flow, it may not be much of an observable. I mean, you may still have the difference, but it's even more significant and really affecting the pressure distribution, etc. In the case of in the case of hypersonic flows. This is what we mean by the boundary layer. That is the entropy gradient that is in a direction that is transverse to a direction of the flow, which has an impact on the aerodynamics and heat transfer of the body. So here it is shown again, the entropy layer. You can see that. So this region, this entire region, but I've tried to mark with a curly bracket. That entire region between the body and the outer, the region that is marked there is referred to as the entropy layer. So please understand the difference between entropy layer and the shock layer. Shock layer is between the shock wave and the body. Entropy layer is the region of gradient. Wherever you are considering it, the gradient in the along the direction that is almost transfers to a direction of the flow. The difference in entropy or the gradient of entropy is what we refer to as entropy layer. Okay. Now, the last one that we are going to discuss today is the high temperature effects. I'll quickly go through it before we go for discussions. I guess I've taken, 20 minutes. That's okay. So I'll wind it up fast. High temperature effects. Quite obvious, because hypersonic flows are going to have higher kinetic energy, right? High velocity, high Mach number means high velocity means wherever you reduce the flow velocity, this kinetic energy is going to dissipate as heat energy or thermal energy, which means that if the flow is decelerating in some places, you are going to encounter very high temperatures there, because the kinetic energy is tremendously high. One second before I go to the effect of it. This you can readily understand. Actually, we have observed all that through compressible flow also, incompressible flow also. That is, what I've made here is a simple Excel plot, where all that I've done is I just assume static temperature to be 300. Let's assume atmospheric temperature of 300 Kelvin. And let's assume different Mach number or vehicles with different Mach number, etc. So what I started with that 0.5 here, Mach 0.5. So M 0.5, M equals 0.5, and T is equal to T 300. I just calculated T naught by using the familiar relation. T naught by T is equal to 1 plus gamma minus 1 by 2 M squared. So it comes out to be what, for 305 or something. Just few Kelvin higher than the static temperature. So that is about at Mach 0.5. And similarly, I've done the calculation for 1.5, 2.5, 3, whatever, 4, 5, then 10, 8 here, and then 10, Mach 10, okay, and then 12, etc. And then correspondingly for each of these, I've calculated the corresponding stagnation temperature. So it is 305 here, slightly higher than static temperature. But by the time you are 4, it becomes 1000 Kelvin, right? And for 5, it becomes close to 2000. And say Mach 8, the stagnation temperature is 4000 Kelvin. Okay, Mach 8. That is, if you bring down Mach 8 flow to to stagnation state, you are going to have a temperature of 4000 Kelvin. If you bring 12 or rather Mach 12 flow to standstill to stagnation conditions adiabatically, you will end up with a huge temperature 9000 K, where your atmospheric temperature, that is starting from a static temperature of 300 Kelvin. So that's a kind of high temperatures that you will encounter in hypersonic flows. So when you consider, again, we just mentioned about boundary layer, etc. Within boundary layer, anyway, the flow is going to come down to 0 velocity, right? At least close to that within the boundary layer. So when the velocity is low, temperature is going to be high, and temperature is really going to be very high in supersonic flow, such that some of these effects are going to be prominent. So when the temperature becomes 800, the molecular vibration will become important in the gas. So you have air molecules. We know that molecules always are in kinetic form. They always possess translational energy. That is, they keep moving freely back and forth in gaseous form. But when you have high temperatures, in addition to the translatory motion, they will also have significant vibration. So from a mean position. So it'd be a combination of vibration and translation. That is the first thing. So when the temperature keeps increasing. The second one is when temperature goes to say 2000, etc. The oxygen molecules, which are otherwise strongly associated, they will start dissociating. That is, O2 molecule will dissociate to O and O. So which means that you will have the presence of atomic oxygen. You will start having the presence of atomic oxygen in air, which we know is not, we don't have that in lower temperatures. It's always as O2. At further higher temperatures approaching 3800 and 4000, nitrogen, which is a stronger bond than oxygen, even nitrogen will start dissociating. So nitrogen is quite inert per se. But then when the temperatures are quite high, to 4000, etc., the nitrogen bond N2 will also start dissociating, and worse still, there will be forms of nitric oxide, etc., NOx formation, because there will be atomic oxygen. The dissociated nitrogen will react with that, and you have formation of NO. So these are things which will happen at 4000. And when the temperatures are further high, you may have the ionization. Ionization means formation of charged ions of oxygen and nitrogen. So O plus, N plus, etc. So the ionization of the gas also will happen when the temperature keeps increasing. So in a typical hypersonic flow field, you can expect all these. That's why I showed this picture earlier. So we know that the temperature, even with Mach 12, the temperature can go as high as 9000. In fact, this is a simplified calculation because I've assumed perfect gas, etc. And there will be several modifications to that we'll discuss later. But this just a simplified calculation just to give you a feel of it. So Mach 12 can entail temperatures as high as 9000. Okay, so these are some of the important effects that are characteristic or that characterize hypersonic flows. Now, in hypersonic vehicles, in their design and operation and analysis, all this will be important. So that's why I've just shown this conceptual scramjet plane. where say you can see in various parts of it, you have viscous interaction, you have shock boundary layer interaction, you have entropy layer formation, etc. And high temperature, of course, all along you will have high temperature effects, etc. So these are all going to be integral part of any real life application of hypersonic flows. I stop here. I'm putting a full stop. Please, I pass on to you. If you have questions, please ask right now. Otherwise, I will also mention about some group formation, etc. for further classes. Yeah. So first thing, your questions, please.
Excuse me, sir.
Please.
So can you go to one of the previous slides? The one with the bow shock. Yeah, this one. So here, we marking a small region as entropy layer, right? Won't there be an
Yes.
entropy gradient in the within the shock layer too? Because it's still a bow shock, right?
Yeah, you are very correct. Actually, what is shown there is a possible region. That is so. Unlike a shock layer, entropy layer is not a well-defined region. So when I say shock layer, I can identify two well-defined boundaries. One is the shock itself, and the other is the body surface. Okay. Whereas when I say entropy layer, what I mean is at a given location, the gradient in entropy. So it can span across the entire shock. What you said is correct. But what there is just in the schematic diagram there, they have just highlighted a portion where there is a gradient in entropy. That's all. Otherwise, the entropy gradient, actually the layer spans all over across, where the gradient may keep reducing as you go away. But then you will have more prominent effects near the wall. And that's what I mean. So any region that you take, you can identify a region where you can, with whatever thickness that you have in this one, you can consider the layer thickness at that location.
Okay, so that's just
It's like so the point that you raised is very correct. You have gradient all across, or the diagram just simply or just shows an example of a region where the entropy gradients exist. That's all.
okay. Understood. Thank you.
Okay. This I had just left the details of it because of that because I was exceeding the time. But then just keep in mind that the dissociation of O2 is O breaking into 2O, the atomic oxygen, N2 nitrogen breaking to 2N, and starts at 4000 Kelvin. And ionization is formation of O2 O plus N2 N plus. I guess I mentioned them verbally, but shown in the picture also. So these are all chemically reacting flows. And that's the reason why in many of the hypersonic flow analysis, you will see that chemical reactions have to be taken into account. Not so prominent in supersonic flows. Okay, now I'm proposing that in order to make our discussions and interaction, and we will certainly devote a part of the class anyway because of this time splitting and attention span and issues like that. And I want and why I want everybody to be part of the whole thing. Since I don't see you, I should at least should be able to hear from you. So in order to ensure your participation and also engagement, my engagement with the whole class, I would like to have the discussion hours to be actually being used as discussion hours. So what I'm trying to do is and also we will utilize this part of it when we eventually have assignments or team tasks or team presentations to be given, etc. We will make use of this remaining 10 minutes, 15 minutes, etc. for each team or teams to present on different days. So in order to enable all these, that is team presentations as well as group discussions and discussions or even individual discussions like this, what I'm trying to do is I just formed it actually, forming groups of the team of the class. I just the most easiest way or most natural way for me to do is that just by going by the order of the roll numbers. And I've taken this listing from AUMS. I see 22 students as of today, actually, when I took it. So I just grouped them. In fact, the first two teams have 5, and the next 3, 4 each. Because it's 22, so I accommodated 2 people in the first 2 teams as extra. So otherwise, it's 4, 4. The first 2 teams have 5 people each. So what I would suggest is that even when we have discussions, I would ask, or I would invite questions, suggestions, answers, etc. from each group. I may call that group name, I may call the student name. Either way, I would like to have the representation of all the groups, at least, if not all the individuals. In fact, ideally, it should be all the individuals. Okay, but then at least group wise, we should have discussions. Now, discussions could be like questions, clarifications that you seek, or clarification or corrections that you provide, or suggestions that you have, etc. And obviously, when we have team assignments, group assignments, I'll be you following this pattern. So when I say group 1, I just named it as HFT1, hypersonic flow theory HFT, HFT1, HFT2, 3, 4, 5, etc. So we'll use this pattern for team, group, assignment, etc. And I would also like to make that the whole internal assessment should be a part of that is not only the presentations, even the day-to-day discussions. I would like to reflect it in some way or the other in the QA, in the not QA, what you call CA, the continuous assessment process. So I would strongly encourage all of you to be part of the discussions whenever we have anything to be put on to the discussion. Okay. With that, I will now say there were 2 numbers that I discussed today: the Mach number and Reynolds number. Now, can anybody tell me the difference between the 2, or why do we have the 2? Actually, you studied Reynolds number in fluid mechanics, but suddenly in compressible flow, the whole stage was stolen by Mach number. Why that difference? Or first of all, why do we have these 2, or why is that difference? Again, I'll leave it here. In fact, I make it as the first assignment for you. For assignment, not for the entire class. I will go group wise. So I would request the group 1, HFT1, to make a small presentation on Mach number and Reynolds number. You don't have to say a lot of things actually, but at least 2-3 slides, or even 2 slides will do. You just present what you understand by Mach number, what you understand by Reynolds number, and what's the importance of it. Okay, so let that be in the next class. It doesn't take much time. So because there is no new physics, it's all things that you know, Reynolds number and Mach number. So let that be the first task for team 1, HFT1. So next class is today's what? I don't have Thursday or Friday. When do we have next class? Thursday we have, I think. Yeah. So Thursday, I would request you to the first team to take 5 minutes, 5-6 minutes. It doesn't take much time. You don't have to strain a lot. Now, it is perfectly all right to me if you say that. Yeah, that is you present what you have, but you say that no, we are not sure about this part, or we need more clarification. That is perfectly all right. I'm not expecting that. I'm not expecting that you should teach the entire class about what the topic. In fact, it's just a discussion. So what you know, you just tell. If you have doubts, if you have points which are not clear, then let's take it up in that question. So I'll try to, as much as I can, I'll try to throw light to it. So this is not to test your knowledge at all. It's just a reflection of, or just to make you think of it and to present what you can gather. That's all. So maybe 2 slides, max 3 slides. You can just state what is Reynolds number, what is Mach number, what is the significance of each of them. Okay. We will take up that in the discussion our next class. Is that okay? By the way, HFT1, is that okay with you?
Yes, sir.
Yeah. Okay, great. Any other questions from anybody?
Sir, one question, sir.
Please.
Sir, can you go where you showed that hypersonic vehicle? That slide. Yes, sir. Here the fuselage is flat and the engine is mounted on the belly. Instead of this, can we do like a ramjet engine, sir? A cylindrical fuselage and the engine nacelle is surrounding the fuselage.
You can actually, this will be, in fact, they have tried both. And as we know, this is all laboratory tests so far. But then the results so far are more in favor of 2-dimensional, or rather planar configuration. That is like this, instead of, so that is one reason for that is this, what I mentioned as the engine body integration problem. So it is found that when you have a planar body, the integration is easier, stability is better, etc., based on the laboratory tests. So that's the reason where, though they, I mean, all our models and they are being studied, etc., you tend to see more planar bodies or 2-dimensional or rectangular kind of structures in supersonic, hypersonic vehicles.
Okay.
It's more related to the aerodynamics and stability.
Okay.
Okay, then so we'll stop here for the day. We'll meet in the next class. Okay. Thank you. Thanks to all of you. Bye.
Thank you, sir.
Thank you, sir.
Thanks.
Thank you, sir.
Thank you. Thank you. Thank you.
Excuse me, sir.
Please.
I'm sorry, I'm asking this very late, sir. But sir, in case of transition from supersonic to hypersonic flows, how will we account for the change in flow characteristics from inviscid to viscous flow, sir? In case of
no.
Yes, sir.
No, that it's an important question. Actually, say what I mentioned was that in supersonic flow we did most of the analysis based on inviscid assumption.
Yes,
and in hypersonic flows, you may not be able to stick to that all the time. Okay.
yes,
So
sir.
which means that when you are actually designing a hypersonic vehicle, you should consider the viscous interaction also. So you because the whole thing, supersonic vehicle, hypersonic vehicle has to operate at hypersonic velocity, right?
Yes, sir.
Which
Yes,
means
sir.
that you cannot assume, or you cannot make it purely based on inviscid assumptions.
Okay, sir. Okay.
Okay.
So what I was trying to ask is that in case of the transition, will both assumptions be valid at that state?
No, it's like that. You can consider it like this. It's not a sudden transition, right?
Yes.
Say hypersonic, as I mentioned in the first, this one. It is like as the flow gradually becomes hypersonic, the
Yes.
viscous effect gradually become prominent, etc. Okay, so
Okay,
it's not
sir.
a sudden transition. So, but as the transition becomes, the effects will be more and more prominent. That's all.
Okay, okay.
So nothing dramatically happens. It's over a range of Mach numbers. It's a continuous process.
All right. Okay. Thank you, sir.
Thank you. Bye.